Hello guys, welcome to this new tutorial on Semantic Text-to-SQL, an AI-powered system that transforms how we interact with databases using natural language. In this tutorial, I'll teach you how to talk with your DB by combining the power of a SQL precision, advanced fuzzy matching, and the intelligence of vector similarity search, just like a RAG system, to create a unique advanced system that understands not just your words but your meaning. I'm so excited to take you on this journey where we will build this entire system from scratch without using any frameworks or pre-built solution. Why from scratch? Because I want you to truly understand every component, every decision, and every line of code that makes the system work. By the end of this tutorial, you won't just know how to use it, you will understand the underlying principles and be able to adapt it to your own project. So, before we dive in, you can download the complete working code from my GitHub repository, the gradient path. The link is in the description below. You will find everything there, the database schema, the Python code, Docker configuration, and detailed documentation. So clone it, run it, experiment with it, and make it your home. Here's what we will cover. First, we will introduce the concept and core architecture. Then we will explore the agentic workflow that orchestrates everything. Next, we will set up the database infrastructure with Docker and PostgreSQL. After that, we will run a comprehensive demo with 30 test questions. Then I will walk you through the prompt engineering that teaches the AI to generate perfect SQL. Finally, we will dive deep into the code itself, explaining every method and design decision. Don't forget to like and subscribe. It really helps me create more content like this. Drop a comment too if you have questions or want to see more advanced AI tutorials. So now let's get started. So imagine combining two of the most powerful AI technologies, RAG and Text-to-SQL, into a single system. A system that can not only understand your questions, but also search, interpret, and reason over the structured data stored in databases. Traditional text-to-SQL systems were a solid first step. They made it possible to ask database questions in natural language, but they still depend on exact words, strict syntax, and perfect spelling. If you misspell a name, phrase something differently, or ask for a concept that doesn't exist as a keyword, they often return nothing, or worse, generate an invalid query. This system actually is built on 3 layers of intelligence: SQL filters for structured, numeric, or database data, fuzzy matching to handle typos and small variation in names or titles, and vector embeddings to understand the meaning, relationships, and abstract concepts. The system also includes multi-language support, automatically translating user questions from any language into the target database language, currently English, ensuring that users can ask questions in their native language and still get accurate results. But it doesn't stop there. The system also includes 2 essential safeguards for real-world use. The first one is the query validation that automatically blocks unsafe or destructive queries, such as insert or drop commands, ensuring read-only and secure operation. And retry mechanism intelligently generates failed queries by analyzing previous errors, learning from mistakes, and producing a corrected version automatically. And with Semantic Text-to-SQL, you can finally explore your data the way you think, naturally, flexibly, and without worrying about syntax or errors. Now let's dive into how Semantic Text-to-SQL actually works under the hood. When you ask a question in natural language, whether it's in English, Spanish, or any other language, the system doesn't just translate your words into SQL. Instead, it follows a sophisticated 5-step process that combines multiple AI techniques to understand, validate, and execute your requests safely and intelligently. So the step 1 is the SQL generation, and this is where everything starts. So the system first analyzes your intent using a specialized large language model. It doesn't just look at your words, it understands what you are really trying to find, that it makes a crucial decision which strategy will work best for your specific question. If you are asking for exact data, like books published after 2020 or products under $50, it uses the SQL filters. These handle structure, numeric, and date-based comparisons with precision and efficiency. What if you misspell something? If you type, for example, Horwell with 2R instead of Horwell, traditional system will fail. That's where fuzzy matching comes in. Using Levenstein distance algorithms, it can handle typos of 1 to 3 characters, normalize text with case-insensitive matching, and even rank results by similarity. For conceptual questions like find books about totalitarianism or show me dystopian novels, the system switches to vector embeddings. This is where semantic understanding really shines. It doesn't just match keywords, it understands meanings, relationships, and abstract concepts. For complex queries that need multiple approaches, so the system combines all three strategies: SQL precision, fuzzy flexibility, and semantic depth to give you comprehensive results. So once the strategy is chosen, the system generates an SQL query with placeholders for any parameters that need to be filled in later. So the step 2 is the validation, okay? And this is where security meets intelligence. Before any query touches your database, it goes through rigorous securities check using a SQL Glot. The system ensures that only select queries are allowed. No insert, update, or drop commands can slip through. It blocks SQL injection attempts and filters out dangerous keywords that could compromise your data. So, if the validation fails due to a security issue, the query is immediately aborted. No retries, no second chances. But if it's a fixable error, the system moves to its retry mechanism. So we go back to the step 3, and you can find it here, is the embedding generation, but only when needed. If your query requires semantic understanding, the system extracts the search terms and calls the OpenAI API to generate 1536 dimensional vector embeddings. We are using that specific vector. These vectors capture the meaning and context of your search terms, not just the words themselves. The system then formats these vectors and substitutes them into the query placeholders, creating a query that can search by meaning, not just by exact text matches. The step 4 is the query execution, and we can find it here. It's where the rubber meets the road. The system connects to your PostgreSQL database, performs manual parameter substitutions for complex queries, and executes the SQL. If the execution succeeds, it fetches the result as dictionaries with column metadata and row counts. But if something goes wrong during the execution, the system captures detailed error informations, the PostgreSQL error message, query context, and parameter details, and adds this to the attempt history for the retry mechanism. So the step 5 is the answer generation, bringing it all back to human language. So the system formats the results, skipping embedding columns and limiting output to 20 rows for readability. Then it uses another LLM to generate a natural language response that puts the query results back into the context of your original question. The result, a human readable answer that feels like you are talking to a knowledgeable database expert, not a computer. But here's what makes the system truly intelligent: the retry mechanism. When a query fails, the system doesn't just give up, it analyzes the error history, learns from previous attempts, and regenerates the SQL with comprehensive feedback. It can retry up to 4 times, learning and improving with each attempt. Only after 4 failed attempts, you can see here, every time it's going back to the beginning when it's generating the SQL, only after 4 failed attempts, the system returns a detailed failure response, giving you insight into what went wrong and why. This entire process just happens in seconds, but it represents a fundamental shift in how we interact with the databases. Instead of learning SQL syntax, you can ask questions the way you think, naturally, flexibly, and with the confidence that the system will understand not just your words but your meaning. So now let's look at the foundation that makes semantic text-to-SQL possible, so the database architecture and how it all comes together. So we run the Docker Compose app, create our DockDB, and it started. We activate our virtual env in Python. We already install all the requirements here, and we have our container ready, and it already create all our table and also all our database rows. You can see here we have a new container, that is this one. Here our container is created, and it's semantic text-to-SQL. That is the vector extension here that we can file initdb SQL for the embeddings, and the FATSI string match here for Levenstein distance FATSI matching. So the database structure actually is designed. This is just an example, of course. You can create your own database, and you can connect with external service, external Postgres database. Anyway, this is designed around 5 core tables that work together to support all 3 search strategies. So we have the authors table, include everything from basic information to rich metadata like literary style, description, or biographical informations. And then we have the publishers table, stores comprehensive information about publishing companies, including their focus and company descriptions. We have categories that have detailed description and typical content description, both with vector embeddings. We have a book table, is the heart of our system actually, that containing bibliographic information, book descriptions, detailed summaries, and table of contents, all with vector embeddings. Finally, the reviews table here capture reader feedback and ratings with detailed analysis. The sample data demonstrate the system capabilities with more than 30 authors here. It's going to generate when we initialize the container. 20 publisher, 15 categories, and more than 70 books. The vector embeddings are what made semantic search possible. Every text field, as you can see here, like in publisher, but also in books, every text field that could benefit from semantic understanding has a corresponding vector column. So you say detailed summary and detailed summary embed, description and book description embed, and many others. So when you ask for books about totalitarianism, the system searches for the concept of totalitarianism, which might appear as authoritarian control or government oppression or dystopia. Actually, when we start our container, we initialize this table and create rows with empty vectors, with all null in the vector, because we are going to compile, we are going to create the vectors in a second step with a specific script that is inside gen embeddings py. Once your database is set up, you run Python gen embeddings py and discover actually all the text fields that have a corresponding embed columns, and scans the database for rows where text exists but embeddings are missing, and generates the vectors using OpenAI's text embeddings tree small model. It updates actually the database with the vector values in Postgres vector format. For example, if you have a book description like a dystopian novel about government surveillance, the script generates a 1536 dimensional vector and stores it in the book description embed column. This process typically takes a few minutes. Once complete, the system can perform semantic searches across all your text content. The process is finished, and after this, let's go back to our schema. Another important concept is the foreign key relationships that ensure data integrity while enabling complex queries. For example, books are linked to authors, publishers, and categories, but the relationships go deeper. A book's semantic understanding is enhanced by its author's literary style, its publisher focus area, and its category's typical content description. So you can find the connection, actually the relationship one-to-one, directly here. The references, like books is connected to authors with the author ID, publisher categories, and many other constraints specific for this case. And we create also some index to speed up the queries. The result actually is a database that doesn't just store information, it understands it. When you ask a question, the system can search across multiple dimensions simultaneously, combining structured data like publication dates with unstructured content like book description to provide comprehensive, intelligent results. So now let's see Semantic Text-to-SQL in action with a comprehensive demo that showcases all its capabilities. We have prepared 30 carefully crafted test questions that push the system to its limits, testing every aspect of a three-layer intelligence we have built. In the repository, you can find all the questions in this markdown file, and they are divided by concept: basic fuzzy matching, semantic search, combined fuzzy plus semantic questions, aggregation and statistics, and we will just test some of them. So first of all, we start our agent with py.main.py. We have our interactive chat that asks for a question. Let's try. So let's start with the basic fuzzy matching. These are typo tolerance. Actually, test typo tolerance with questions like find all books by George Orwell, where the system must use 11 side distance to find George Orwell with just one R, despite the spelling error. The system calculates character differences between the user's input and the database values using threshold of 2-3 characters for short strings and 5 for longer one. It orders a result by similarity distance, showing the closest matches first. So this ensures user get results even when they misspell names, titles, or categories. Let's try. You can see all the log, generating the SQL query. This is the query. As you can see here, it applied the Levenstein, make it lower, and the step to executing the query, generating final answer. And here we go. We have our final answer. Here are the books by George Orwell, and we have the list. Cool. Let's try the next one. All the same with a typo. Show me the book title 1984. Let's see. Or maybe let's try this one. What books are published by Penguin Random House? Actually, it's a mistake. Let's see. SQL query. It also add Levenstein here. And here we go. The books published by Penguin, not Penguin, and not Penguin, not Penguin. And we have all our books here. Okay, this is the SQL. See, it's a well-formed SQL, not a little bit complex. It's not that easy, right? But the model is creating, because we will see we create a really powerful prompt that help us to create something like this. We are using the OpenAI 4.1 model that is really powerful, and the output for this specific case are really good. So let's try the semantic search, the next type, so the next group. Actually, this question challenges the system with conceptual queries like find books similar to 1984 about dystopia, where it must understand the meaning of dystopian themes, not just search for exact keywords. So the system generates the dimensional vector embeddings for the user search terms using OpenAI's text embeddings. It then uses cousin similarity to find the most semantically similar content in the database. So this allows the system to understand concept even when the exact words doesn't appear in book description. Let's try this question. See how it works. Here we go. Generating query. This is the query. It's going to execute the query and generating the final answer. So this is the query. As you can see here, we are performing a vector search here. This is the special command in the Postgres with the vector extension, and find for using the similarities from books, where books description embed. So it's using our embedding that we created before. Remember, with the gen embeddings, we populate all these fields and order by similarity, limit 15. Wonderful. That's really cool. It's telling us that we need embedding, because if we need embeddings when we receive the SQL query, before performing the SQL query, we need to calculate our embedding from the user request to perform the similarity search. And we got all the rows, and here we go. So here are some books similar to 1984 that explore themes of dystopia and government control. And it's really interesting answer. We can find directly all the books here. The Handmaid's Tale by Margaret Atwood, Fahrenheit 451, Never Let Me Go, Animal Farm, and many others. These novels, like 1984, focus on oppressive societies, loss of individual freedom, and dangers of unchecked power. That's cool, right? So let's try another semantic search question. Something, for example, which publisher focus on children's literature? That's a pretty interesting question because we are going to analyze the publishers. Go. Query. We get our SQL. Here we go. This is the generated SQL. Also the same. We get our embedding similarity search, comparing vectors, limit our first similar rows. In RAG, we call chunks. In this system, we call rows. We call a specific description text. There is a specific field that match with embed. So when we get the similarity search, we are going to retrieve the relative field that is text. In this case, we are going to take the publishing focus description without embed. And here we go. The following publishers focus on children's literature. Scholastic Corporation specializes in children's and youth adult books. Hackett Books Group, Little Brown Company, and many others. So let's go to the next group. The next group is combined FATSI plus semantic. That things are getting interesting and more complex. Actually, this shows the true intelligence with questions like, for example, find books by Margaret Atwood about dystopian societies, where the system handles both the typo in the author name, okay, and the conceptual meaning seamlessly. So the system first applies the FATSI matching to find Margaret Atwood despite the typo, then uses semantic search to understand dystopian societies as a concept. So it combines both strategies in a single SQL query, both using AND logic to ensure results match both criteria. This demonstrates the system's ability to intelligently choose and combine different search strategies. So let's try. Find books. Margaret. Okay. Let's try generate SQL query. Go. We get our SQL query. There we go. This is the generated SQL. Let's analyze the SQL. So we have a select. First of all, the LLM choose what fields are important to answer our question. So title, publication date, first name, and everything. We get the book description, embed similarity search from books, and join authors on author ID. That is going to be the same. So we're going to join all the author with the books that we find, where level style lower, so first name Margaret is smaller than 2, and level style lower at last name Atwood is also smaller than 2. So this is quite complex SQL query, but actually it's what we need to answer this specific question. As we can see here, with embedding, we retrieve all rows, the final answer. So Margaret Atwood has written several books about dystopian societies. Notable examples include The Handmaid's Tale, set in totalitarian society where women subjugated and used for reproduction, Horrocks and Craig, The Year of the Flood, The Testaments. That's wonderful. Yeah? That's really that works really good. Let's go to the next group, that is aggregation statistics. So this text is a complex SQL generation with questions like how many books did Stephan King write, combining FATSI matching with count, average, and group by operation. The system must first handle the typo here. Here we go. Stephan King wrote 4 books according to the available data. We can find the query here. That's great. So let's try another question in this group. For example, average price by category. What is the average price of science fiction books? That's quite interesting. The average price of science fiction books is about $15. That's cool, right? Select average. You can see all the query here. And it's also using level style to match the category name. That's cool. And let's try another statistics, like which publisher ever released more than 5 books. There are no publishers who have released more than 5 books, of course, because we have only 70 books and we didn't add more than 5, so that's correct. Let's find the top rated books. Body text, average rating plus order. Here we go. That's cool, right? Here are the top 10 highest rated books based on reviews. Midnight, 1984, And each of these books I received a perfect average rating of 5. That's okay. So let's go to the complex filters. This is another group that is a challenge multi-criteria queries like find books priced between 10 and 20 published after 2000. Let's see what happened. Actually, test date ranges, price ranges, Boolean conditions. So the system must understand multiple filter conditions and apply them correctly using AND logic in this case. Here we go. We have our books with all the price here. Some books priced between 10 and 20 that are published after the 2000. That's wonderful because it shows us here and the price, here and the price. There are a total of 21 books. You see how fast it is? The next group is advanced multi-table queries. So let's try this one. Which author has the most book published by Penguin Random House? That is actually author plus publisher plus stats. Here we go. We have one row. So as you can see here, this is the query. The author with the most books published by Penguin Random House is George Orwell with 4 books. Go. So let's go to the last group. That is the final monster is the ultra complex combinations. Represent the ultimate test with questions like, for example, compare books similar to both 1984 and Brave New World written by authors with names ending in well or lay. Published by publisher focusing on literary fiction, price between 12 and 18 with reviews mentioning social commentary. That's quite complex. Let's see what that is. Generating 6 embeddings, 6 similarity search. So there are no books that match all of your criteria similar to both 1984 and Brave New World. It's too complex. Look at the query. Look at the SQL query, how complex it is. And it's perfect. Let's try this one. Show me dystopian books similar to the Tale published, founded after 19. Let's see if we find. So here we go. Also in this case, we didn't find it. It's too specific and we don't have any book that matched this criteria. Now let's dive into the sophisticated prompt system that powers Semantic's Text-to-SQL. The ability to generate perfect SQL queries from natural language. Actually, I want to start from the prompt because it's the heart of our system. Later, after this, we are going to analyze all the code line by line and every files. But now I want to explain how the system prompt works. So this is just a simple prompt, as you can see here. It's a carefully engineered system that combines multiple AI techniques with deep database knowledge to create queries that are both powerful and safe. First of all, we give the role. You are a professional SQL query generator for a Postgres database with pgvector support. The database schema we inject here, but actually we have a preview here in this txt. So this is what we're going to put into the prompt, the database extraction, every single table, authors. We explain all the columns, the type, if it's a primary key, not null, and everything, the constraint, and all the foreign key, and everything here. And at the end, we have the relationship summary. Authors referenced by books. Books are references by as references to authors, publisher categories, and they're referenced by reviews. So it's really complete. It gives like a panorama of how our database is structured and all the data relation. After this, there is the decision engine. Okay, is where the real intelligence lives. The prompt includes a sophisticated decision guide that teaches the AI when to use each of our 3 search strategies. Question with explicit similarity intent, find books. We have some just small example, questions with semantic conceptual content. So find books about adventure, publisher that focus on science fiction. It tells to the LLM to use similarity search because you need semantic understanding. Question with both semantic plus filters, question with only explicit data. In this case, you have to combine similarity search and traditional filters. In this case, you have to use traditional SQL only with no embeddings needed. And it knows to use vector embed. So for explicit similarity requests, like find books similar to 1984, it knows to use vector embeddings. For conceptual searches like books about adventure, it understands that semantic understanding is needed. For exact data like books published in 2020, it knows traditional SQL is sufficient. We have the translation layer. and is here. All data values in the database are stored in English. You can see category names, and actually, and as one of the most complex challenge, multi-language support. So the prompt explicitly tell the AI that all database values are stored in English and provides clear translation rules. When a user asks, for example, in Italia, trova libri di fantascienza in Italian, the AI knows to translate fantascienza to science fiction before searching the database. We have also the fuzzy matching logic, and is here. Is incredibly sophisticated. So the prompt teaches the AI to use Levenstein distance with different thresholds based on string length. 2 characters for short strings, 3 for medium, 5 for long ones. It knows to apply this to author names, book titles, publisher names, and categories. Always order results by similarity distance. The vector embedding system that we can find here is where the semantic understanding happens. The prompt explains that fields ending with underscore embed are vector columns and teaches the AI to use distance operator with proper placeholder syntax. It knows to check for null values and use correct Postgres vector format. We have the safety mechanism are built right into the prompt, so the AI learns to always use limit clauses with a hard maximum of 100 rows unless the user specifies otherwise. Understand the group by rules for PostgreSQL, knowing that vector columns cannot be included in group by clauses. The output format, that's really important because it ensures consistency and reliability. The prompt requires the AI to return structured JSON with 3 fields, the SQL query, whether embedding are needed, and the specific parameter for embedding generation. This structured approach allows the system to process the response programmatically. The example section is like a masterclass in SQL generation. The prompt includes more than 20 detailed examples covering every possible scenario, from simple author searches to complex multi-table queries with dual semantic searches. Each example shows the exact input, the reasoning process, and expected output. When the queries fail, we are using this create SQL retry prompt. The system feeds the error history back to the AI with specific instruction to analyze previous attempts and avoid repeating the same mistakes. This creates a learning loop that improves with each failure. So the result is a system that doesn't just generate SQL, but it generates intelligent SQL. It understands context, handles edge cases, maintains security, and learns from mistakes. Now let's dive into the code architecture, understanding how each Python file works together to create this intelligent system. I will walk you through the actual code, explaining every important part line by line. So the semantic text-to-SQL is built on 4 core Python files working together like a well-coordinated team. So the first one is the gen embeddings, you can find here, and actually it prepares your data by converting text into vector embeddings. Spy, extract and format database schema information. Text-to-SQL agent is the brain orchestrating SQL generation, validation, and execution. And MainPy provides the user interface to interact with the system. Let's start with the execution flow, beginning with how the agent initializes. So the text-to-SQL agent. This is the agent class, okay? Agent text-to-SQL. This is the heart of our system. When you create an instance, it sets up everything needed to convert natural language into SQL queries. Think this as a translator that sits between you speaking natural language and your database that understand only SQL. So it needs 3 pieces of information to work. So how to connect to OpenAI's API, how to connect to your database, and what your database structure looks like. First of all, the full configuration is provided so beginners can get started quickly without knowing database details. And while advanced user can override everything, the temperature value of 0.1 is carefully chosen. Higher value like 0.7 or 1 make the AI creative, which is great for writing stories, but it's terrible for SQL generation because you want the same query for the same question every time. So we check the API key before looking the database schema, because the API key, of course, is missing. We want to fail immediately with no point in loading schemas if we can AI anyway. Storing the schema in memory after loading it once means every query reuses it, which is efficient. If your schema changes, you just create a new agent instance. So when you run agent text-to-SQL, your real-world usage, here's what happened in milliseconds. Python creates an object and calls the init method that actually set model to GPT 4.1 and the temperature, calls the initialize OpenAI client method, which checks the API and creates the API client, then calls load database schema, which connects to the database and extract all table info, and finally returns a ready-to-use agent that remembers everything. The agent now knows how to talk to OpenAI and understand your database structure. Initialize OpenAI client. This method actually ensure, as we saw, to securely connect to OpenAI using your API key. And we have the database schema loading with load database schema. This method uses the utilities module to extract and format the complete database structure. Understanding your database structure is absolutely essential for the AI to generate the correct SQL queries. And so the formatted text that gets stored include everything in a clean, readable format that AI can understand. Table names, column times, we already saw, and you can find it here in db schema txt in this file. And so let's go to the main pipeline. So the process request with execution method. It's here that we run directly from the main after we initialize. After we initialize the class, we just call this method and we give as a parameter the user query. So this is the orchestrator method that handles the complete flow from question to answer, including retry logic. This is where everything comes together. It's the conductor of the orchestra coordinating SQL generation, validation, execution, and answer formatting, all while implementing intelligent retry logic that learns from failures. So, as you can see here, this method implements intelligent retry, where each failed attempt provides feedback, to improve the next one. So the beauty of this approach is that the AI doesn't just blindly retry the same thing, it learns from each failure. So the first step is generate. So for each attempt with a maximum retries of, we set at 4 as a default, the first attempt is going to be generate, is going to invoke generate SQL. So this method actually sends your question to OpenAI, and we can find it here, and gets back the structure SQL. This is where the natural language magic happens. So your English question gets converted into precise SQL that the database can execute. And it's using the prompt that we just analyzed before. And the response format parameter actually ensures that we always get valid JSON with no parsing errors. This is a relatively recent OpenAI feature it's incredibly useful. Before this existed, you'd have to parse free-form text and hope the AI followed the instruction to return JSON, which was error-prone. So now we tell the API only return JSON, guaranteed form JSON every time. So the placeholder count validation actually is important, because if the AI generates SQL with 2 vector placeholders but only provides one embedding parameter, the query will fail during execution. We catch this early with a warning, so we can see it in logs and potentially retry if needed. So after generate the query, we have execute SQL. And before any query runs, this method checks for dangerous operation. Let's see the function here. And as you can see here, of course, security is paramount when you are letting an AI generate SQL queries, because one malicious or incorrect query could delete your entire database, modify critical data, or expose sensitive information. So this validation actually, this method implements defense in depth, multiple layer of checks that all have to pass before a query is allowed to execute. So we get all the statements here. Each check actually define actually the operation that could modify or damage data here. Insert, update, it verify that the query start with select. This is positive check, so we don't just block bad things, we verified it's select. That strip or remove actually the white space first in case there are spaces or new lines before select. And after this, we have also group by, actually check for vector columns in group by that can causes Postgres error. For example, Postgres cannot group by vector columns. They are too complex. So if AI try this, the query will fail, so we catch it early. After this, we have additional validation using SQL Glot parser. We replace PG vector operators with standard operator for parsing because actually SQL Glot doesn't understand Postgres vector operators. We temporarily replace with plus just for parsing validation. And in this part here, we parse the SQL query using the PostgreSQL dialect. Okay, so SQL Glot parse one converts SQL string into an abstract syntax tree, AST. AST actually is a tree structure representing the query's logical structure. So when semantic search is needed, this method creates vector embeddings. Embeddings are actually the secret sauce that enable semantic understanding. As we can see here, this function, go directly here, and there is two functions. So each semantic search require real-time embedding generation. So this function here, actually, we need to maintain actually the order. Embedding one goes to place order one and process each embedding parameters in order. So embedding param is a list of dictionaries, each containing text to embed, description, and placeholder, as we saw on the prompt. So it extracts actually the text that needs to be embedded. These are the key concepts that we want to search for semantically. And after we call the helper method that is generate embedding for the actual embedding. So this makes an API call to OpenAI that returns list of floats, the API call from the client using embedding. We define the embedding model and the dimensions here. And after this, we have this line that actually convert to Postgres SQL vector format. PG vector extension expect this specific format. We convert Python list to string with brackets and comma separated values, and with the map string embedding converts each float to string, and add to our list of embeddings. It append in order, and at the end you return all the embeddings as Postgres SQL format strings. So going back to execute SQL, actually after the validation, what happened here? After the validated SQL query, so if it's not valid, actually determine if this is a security issue or just a syntax error. So if security issues like dangerous operation that should never be retried. And if our syntax error actually are fixable problems that can be corrected on retry. If validation passed, it's safe to connect to database. And we connect with our configuration, and actually it creates the actual TCP connection to PostgreSQL server. After this, it create a cursor. This is what actually execute queries. And after this, we have generate embeddings if need only for semantic searches. So if need embeddings, we generate all embeddings by calling OpenAI API. This might take max from half to 2 seconds, depending on how many embeddings needed. It return a list of PostgreSQL formatted vector strings, okay? And here, handle the parameter replication. So sometimes AI reuses same embedding, like field, other. Actually here, it count how many placeholders exist in the SQL. So if actually more placeholders than embeddings replicate cyclically, and here actually we replace each parameter with actual embedding one at a time. And after this, we execute the query with parameters substituted. And in this other case, if no parameters needed, simply select query without semantic search, so just execute direct. Here it fetch results from the executor query, fetch all, return all the rows as list of tuples, and after this we get the column names, okay, from cursor description. Dot description actually contains the metadata about the returning columns, and it convert, okay, after this result list actually convert to list of dictionaries for easy access. Tuples are hard to work with, so dictionaries let us access by column name. In this part actually create dictionary mapping column names to values, And after this, we just clean up the database resources. Always close cursor and connection when so failing to close can exhaust the database connection. And at the end, it just returns structured result with all information. Success true. Let's see how it works the regenerate SQL with error feedback. In this case, we call this function when we get an error. Okay. We create a system prompt here with database schema, the same prompt as the initial generation. The AI needs the schema again. Actually, it built a comprehensive error history here to send to the AI. This is the crucial part. We are teaching the AI what not to do actually. It starts with an empty string. So here, for each attempt, this gives the AI complete context about what failed and why. And after this, here we create a detailed retry prompt with all previous errors, creates SQL retry prompt is defining prompt PY as we saw before. It creates a message that says, hey, here's what failed before, don't repeat these mistakes actually. And at the end, we call OpenAI with error feedback. This is similar to generate SQL, but with enriched context. We have the response text here, and after this, we convert JSON string to Python dictionary, and it returns at the end the regenerated result. This should hopefully fix the errors from previous attempts. If it doesn't, we'll add these attempts to history and try again. And let's see the last step, that is final answer generation. So actually, this method converts the query results into natural language. So after all the work of generated SQL, validating, executing, and fetching results, we need to translate those results back into human-friendly language. So the user has a question in English, they deserve an answer in English, not a raw table of data, of course. And here, actually, we format the result as a text for the process. Case 1 actually is query execution failed. Extract the error message and format. This tells the answer generating AI that something went wrong. And the case 2 actually is the query succeeded but returned no rows. And case 3, query succeeded and returned data. So it starts with a summary of how many results we got. And after here, show first 20 results, limit for readability and token usage. But we can change this parameter because we slice this at 20, the first 20 items. And after this, we have these 4. We add actually in this case a header for the result and iterate through each column in these row items, gives us column name, values, and pairs. And here, actually, key value, actually, we skip the technical column for readability. Embed column are actually not useful to show to user, of course. We have similarity score of technical metrics, so we skip them too, this part. We only show human readable columns like a title, author, price, and others. And at the end here, actually, we add a blank line between results for readability. And if we have more than 20 results, indicate that don't show all 100 results, too much text, was the tokens are to read, of course. And at the end here, we create the prompts for answer generation, create final answer prompt. You can find in prompt py, and they create the final answer user message. Okay, actually create the final answer, combine original user question, the formatted results, and the optional SQL query for context. But this is a different AI call from SQL generation, same model but different purpose, translate data to natural language actually. And at the end, we extract the natural language answer and we return directly the answer that is a string. Utility extract database structure for the AI, and we see the generate the DP schema. All this function here is just to generate this final output that we put into the prompt. So we have covered a lot in this tutorial. We started with the core concept of combining RAG and text-to-SQL into a unified system. We explored the sophisticated agentic workflow that orchestrates SQL generation, validation, execution, and intelligent retry mechanisms. We set up a PostgreSQL database with vector extensions and populated it with rich semantic data. We tested the system with many comprehensive questions, ranging from simple typos to ultra-complex multidimensional queries. We dove deep into the prompt engineering that teaches the AI to generate perfect SQL. And finally, we walk through every line of code, understanding the design decision and engineering principles that make this system robust and reliable. So the beauty of this system is that it's not just a proof of concept, it's a real working solution that you can deploy today. You can adapt it to your own databases, customize it for your specific use cases, and extend it with new features. So the code is open source, well documented, and designed to be understood and modified. Remember, you can find all the code on my GitHub repository, the link is in the description. Start the repo if you find it useful, fork it to make it your own, and feel free to open issues if you have questions or suggestions. If you enjoyed this tutorial and learned something valuable, please give this video a thumbs up and subscribe to the channel for more advanced AI tutorials. I'm constantly working on new projects that push the boundaries of what's possible with AI, and I'd love to have you along for the journey. So thank you for watching, happy coding, and I'll see you in the next video.